Welcome again to Physical Science Survey, PHSC101. I failed during the Chapter 1 discussion to introduce myself. I assumed that that would be available in other videos in Blackboard, but I'm Dr. Bly, and let's see, my tag is sort of visible. Today we're going to look at Chapter 2 in your textbook by Shipman and others. And that chapter is entitled Motion. Now you'll notice that the date is the 19th of July, and that's not the date that you're watching it, of course. That's the date I recorded it. So let's move ahead with sharing the PowerPoints first. Let's see, that's not what I had in mind. There we go. And you can't see what's going on here, but hopefully, there we have it. And we're going to go slideshow. Come on. There we go. Now we can move along. Motion. This is a fairly short chapter, but it's packed with a lot of information. So we'll try to get finished within an hour, hour and a half, if at all possible. We're dipping our toes these first few chapters in the topics of physics. And physics, by definition, is the very most basic science in the natural world studies. In other words, we want to understand through physics investigations the basic principles that describe how the universe actually works at the bottom level. And that generally involves mathematics. Can we describe the world in mathematical terms? Mathematicians just say physics is applied math. And of course, physicists say that chemistry is applied physics. And chemists say that biology is applied chemistry. So each one has their own favorite subject. And for our purposes, the very basic level is physics. It deals with things like matter, how things move, the forces that are applied, either static forces where nothing moves, or forces that cause motion, and exchanges in energy that are involved in physical processes. So let's move to the next one. Now, in physics, we can subdivide physics into several categories. We're going to begin with classical physics. And these are, at least for classical physics, we're starting from a historical perspective. The modern sciences relative to physics started with classical physics. And what we mean by that is those are how do things move? What are the mechanics of objects that we can see, that we can handle? And then later, of course, those that we can't handle, but that are very massive, but not so massive that the theories break down. As we discussed in Chapter 1, if you get too big, then the theories and the laws that were developed from classical mechanics just completely fail. So we're going to restrict application of classical mechanics to those areas for which it works. Then we'll look in subsequent chapters at sound and other types of waves, thermodynamics, which is a fancy word for energy transformations in the physical world, electromagnetism, was another possibility. Then we are going to dip our toes a little bit into quantum mechanics, but not too deep, just to get a taste of what we mean by quantum mechanics. And that will happen when we look at the atom. And there again, atomic and nuclear physics go hand in hand with quantum mechanics. Now, of course, ultimately, we end up with topics of quantum mechanics for the very, very, very small, and relativity for the very large and fast. So anything that moves near the speed of light or is very massive, we're talking about relativity. And that naturally invokes the name Albert Einstein. Okay, let's get back to motion. All we want to know is when things are moving, how do they move? I was about to say why, but we're not talking about why here. We're talking about just how do things move. And another fancy term for that is kinematics. In fact, when I took physics in college, we didn't call it motion, it was kinematics, which is a Greek term for the mechanics of motion. Okay, we detect motion everywhere. How do we know that something is moving? If I hold this pen right here, by some definition, I can say that pen is not moving. Okay, how do I know it's not moving? Well, there's no relative change in position. Relative to what? Relative to some frame of reference, like the background, right? Or whatever frame that I create. I could draw a line across here and say it's moving on that line. So for motion, we need a frame of reference. And we'll talk about that as we go. But we're familiar with motion, walking, driving, flying. Obviously, we understand what that means. And we will get to the frame of reference shortly. Okay, so we're going to focus our attention. Once we have our frame of reference, we're going to focus our attention on these three concepts. What is speed? Everybody has a general appreciation for what speed is because those who are taking this course more than likely have driver's licenses, and you may have sped your way to work or some other class. But in scientific terms, velocity is related to speed, but it goes one step further, and I'll describe that in just a second. And then we're going to look at acceleration. What does acceleration mean? All right. We're going to divide the types of motion that we study into two categories. Straight line motion. And sometimes straight line can be a combination, a composite of straight lines. So it could just be a straight line, like a race car down a track. Or it could be throwing a ball at an angle, right? It's a straight line for a while, but it starts to curve, correct? Well, we can divide that motion into two directions. It's moving up for a while and horizontally for a while, right? And we can describe those independently from one another, but they're still straight line for each of the motions that we extract from that one, the simpler motions. And then there's circular motion, right? We know what that is. You just take, well, I don't know. As a kid, I used to tie a rock on the end of a string and swing it around my head, right? That rock was in circular motion. I didn't know what I was doing in physical terms, but now I do. And we're going to talk about circular motion as a separate concept to straight line motion. Okay, so our frame of reference. We've got to define some terms here. What is a position? Position of an object is where is it? What is its location? And for a straight line, the object may be here, right there. Now, if we say that this straight line has a 0 point here, and say, let's just make up a measurement, say 10 meters. 10 meters there. Then its position would be about, 5 meters from the 0 point. Now, the thing that we have to define is, what do we mean by from here to here? Well, we take our cues from mathematics. From left to right, as things get bigger, that's positive. If, however, we have an extension on this side, like that, and we say this object moves from here to here, now we have -5 meters and -10 meters. So to the right is generally accepted as positive, to the left is negative for position. And for motion, for that matter, and we'll talk about that in a minute. But this is our reference system on a linear scale. Now, mathematics also has allowances for 2 dimensions and 3 dimensions, right? If we drew another axis here, right? If you've had algebra, you recognize that as a Cartesian coordinate system. This is X, that's Y. Up and down is positive this way, negative that way. And if this box happens to be over here, we say that it has an X value of, say, 3 meters, and down here probably 3 meters. So its position is 3-3. All right. All right. So we've got the position of our object that we have to consider. Then if the object moves, it's going to change position. I probably shouldn't have erased that. But our object in that example moved from +5 to -5, right? So which direction did it move? I better draw it again. If this is 0, that's 10 meters. Our box is here, and it moves from 5, positive, to 5, negative. All right. There has been some motion from here to here. It's changed position. How much did it change position? Well, from here to here is a -5, and from here to here is a -5. So it changed -10. So we write that as a delta, right? Let me see. I want to be consistent with our variable letters. If we change position, what are we calling that? How did that get upside down? Uh-oh. Yeah. I got a printing error here. All right. S. S is where it is. So that's a 5. And this is its S initial position, and this is its S final position. Okay? So when we want to do a change or a delta S is always equal to final minus initial. So we have this position minus this position. If this position is +5 and it's a minus, and this one is a -5, That's a -5, and a -5 is -10 meters. And that's equal to our delta S, or change in position. It changed -10 meters. So since we know minus is taken as to the left, then we know that it moved 10 meters to the left. And it had to move. I mean, there's motion involved. All right. So how did it get there? Was it instantaneous? I mean, you just go like that? No, it took time to get there. How much time did it take? Well, we don't know, but we will designate it as t equals something. So many seconds. That's our standard unit, is seconds, right? So if we want to know how fast it got there, we know how much distance was covered and how much time did it take. So we have delta S, and then there's how much time did it take. And that has a special value. I mean, a special symbol. If we're not designating direction, then however far it went in that amount of time would be speed. But since we're saying, yes, we know the direction, it moved this way. Speed does not specify direction. So I can drive 60 miles an hour down a straight road, or I can drive 60 miles an hour through a curve and another curve and another curve. As long as I'm covering the same distance in that curve over the same amount of time, I'm doing 60 miles an hour. It doesn't matter what direction. Obviously, if I'm going through a curve, my direction changes. Okay. Velocity says, takes into account direction. So since we know right to left, then we know that the velocity, or V, equals, let's say it took 2 seconds, right? So we have -10 meters in 2 seconds, and that's equal to -5 meters per second. Whenever we use that symbol V for velocity, we are specifying direction. That's the difference between speed and velocity. There's a special name for that. This is known as a vector quantity. Vector quantities always specify direction. Okay, keep that in mind. Okay, speed is a scalar quantity. In other words, the scale, this magnitude of the number is all that matters. So we could say this speed was 10 meters per second. We don't say positive or negative. Right? Or a car going 80 kilometers per hour doesn't say what direction it's going. It could be going straight up for all I know. Probably not. That would be ridiculous, but unless it was in an explosion. But velocity specifies direction. So this is a scalar quantity. Velocity is a vector quantity. It has magnitude and direction. So we would say, for this car, 80 kilometers per hour north, and north would be a positive number. So if we were to say on the Earth surface, we would have to specify direction, say north. We could put a positive out here, but it's understood a positive. If we said negative, then we would say it would have to either be the south or west, because east would be positive, north would be positive, south and west would be negative. So if we said negative, that could be west or south, so we would have to specify. Okay. So vector quantities always have a sign. If there's no sign, it's understood to be positive. And with a negative, you do have to specify. Negatives are always to the left, positives are to the right. And positives are up and negatives are down. So in this case, the velocity of the red car is negative something to the left. And the blue car is positive something to the right, and the person walking is positive v sub m. Okay. Now we have the concept of average. What we have calculated here is an average speed, right? We're saying it took 2 seconds to get from here to here. But we didn't say that there was any change in between. It could have had it could have had taken a half a second to get to here, and then a second and a half to go the rest of the distance. That's non-uniform velocity or non-uniform speed, depending on how you specify. But when we say average speed, we take the total amount of time to get from here to here, and we just average it, right? And for our purposes, average is the best way to introduce the topics, because when you start talking about non-uniform speed, then you get into some more complicated mathematics, and we don't have the time. The course isn't made for that type of approach. We're talking about average values. So the distance traveled divided by the time to travel that distance. That's all we're saying. Now, it looks like the authors are using D for distance. That's fine. Some textbooks will use S for distance, but D, we'll try to stick to the author's use of symbols. D is distance, T is time. V, when you see this bar over a value, that means average. In statistical terms, that means the mean. So if you've had any statistics, you understand that mean means average. All right. So there we have, and then here's a delta t also. Here we had, I just put t up there because we were starting from 0 and we were ending on stopping there, and we just want to know what happened in between. So I use t. But if your object is here already going at a certain speed, and then it goes to here, right? We want to measure the time. So if we're using time on a different reference scale, then this may be a different value of time. It may not be 0 time. It could be some other, but it's still final minus initial gives you the change in time. The distance is the actual path that was taken. All right, so that's what speed means. The actual path, because it doesn't specify direction. It could be through the curve. Now, if you were in an airplane and you wanted to go from point A to point B, the car might have to go through a bunch of curves, but the plane could go straight, right? That's a different distance. Now, here's another concept that sometimes it spins students' heads around. We've talked about average speed. There's also a concept called instantaneous speed. The term instantaneous has its roots in mathematics and in Newtonian physics. Newton worked this problem out from scratch. In fact, he invented a new mathematics in order to help him do that. We call it calculus. But we're just going to focus on this one concept, instantaneous speed. That's the speed of an object at an instant of time. And what that means is the change in time is very small. It's approaching zero, actually. So what's a practical connection that we can make with instantaneous speed? When you're driving along and you look at your speedometer, what does your speedometer say? It says you're going 60 miles an hour. Well, how do you know, right? You looked at it for 0 seconds, instant, and you know that your speed is 60 miles an hour. But the only way to prove that is to measure it from this point to that point, and how much time did it take? Right? So the instantaneous speed is the speed is the distance you travel as t approaches 0. Right? It's kind of a weird thought, but it's useful to think of speed in terms of instantaneous value. Why? Because if we're going around a curve like this, what's your instantaneous speed here? Right? Speed. How about here? How about here? Okay. You may, from here to here, you may average 60 miles an hour. But in order to make that average, you might have to go 70 miles an hour here and 70 there, because in the curve, you're going to slow down. Unless you add more gas, push on the pedal. If you don't do that, then you'll slow down and hopefully come out of the curve faster. Anyway, or you could start out very fast and come out very slow. Your instantaneous speed changes as you go, but the average is 60, right? So the instantaneous speed does tell us something about your travels. All right. So that just illustrates what I was talking about, looking at your speedometer, right? You'll notice that cars now, and have for so many years, been calibrated for miles per hour and kilometers per hour. So if you're going 60, or say close to 65, you're actually 100 kilometers per hour. Now, did your speed change? When you looked at this one on this side and this one on this side, my speed didn't change. It's still 65 miles an hour, but it's also 100 kilometers per hour. Okay, there's the concept of conversion factor. Those are related. You're still moving the same speed, but you're using two systems of measure for each one. So they're equivalent and can be used to make conversions back and forth. Okay, now for velocity. So velocity, we need a direction specified. Right? So the average velocity is still a value of distance, but in this scenario, we're going to introduce another concept called displacement. The average velocity is displacement divided by change in time. Now, what's the difference between distance and displacement? Right? Displacement is a straight line distance between your initial and your final positions. So if we had a speed going this way, then from here, this point A to this point B, this is your displacement. Okay. from here to here is displacement, because it's a straight line. Okay, and obviously the measured amount here is shorter than it is here. So velocity would not be, if the average speed here is 60, then the velocity here would not be 60. In fact, it would be higher, because you had to go a further distance. It took you longer to get there. Well, actually, we're using the same time measurement. It's just the distance is shorter. So this distance and this displacement is shorter than the distance traveled in the curve. So you traveled a shorter, actually, velocity is less, because this is the value of, let's see, what was our term? D. And let's use S for this one. All right, so we keep them apart. This is D distance, this is S distance. So that's smaller divided by the same time. Okay, so that means the velocity is less. Your velocity in this case would be less because the distance was less over the same amount of time. All right, so that's the distinction between distance and displacement. The instantaneous velocity is similar to speed, except now we have direction specified. So you would have to specify some type of direction here. If we were on the surface of the Earth, and that's north, you would say this is velocity v in a northeasterly direction. Or if you're familiar with navigation on the surface of the Earth, this would be 0 degrees, and that would be 45 degrees. This would be 90 degrees, right? This would be 180 degrees. This would be 270 degrees. And then back around 360 is equal to 0 degrees. Okay, so it's clockwise in navigation. And we'll get to that in another chapter. But you would have to specify direction somehow. All right, here's an example. The distance traveled from your hometown to the university is what? 50 miles. What's the displacement? Or you could go this direction. I said, oh, and that's 86 miles. And this is 97 miles. That doesn't look right. That looks like it's a shorter distance, but we'll take their word for it anyway. The displacement, though, is less from hometown to the university, right? Just like our example here. Now we have average velocity. We have instantaneous velocity. What do we mean by constant velocity? Constant velocity is the situation where the average velocity is equal to the instantaneous velocity. That means that wherever you measure along that line, the instantaneous velocity is exactly the same everywhere. Right? So that velocity from here to here, any point along there, instantaneous, is the same value. That's a constant velocity. It does not change. All right? So that's convenient, because you know that if you're going 20 meters per second, then in 1 second you've gone 20 meters. In 2 seconds you've gone 40. 3 seconds, 60. 4 seconds, 40. 80. 20, 40, 60, 80. So that constant velocity is easy for calculation purposes. Okay. So here we have 20 meters per second is the average speed. It's also the average velocity left to right. If we were on the surface of the Earth, we might say east. But we would need a reference for that. If we were to say that, then we would have to do this. Maybe the north goes up here, like that. Okay, then once we have our reference system, we know what to say, what to call it. Okay, how far would the car travel in 10 seconds? Okay, what do we know? Well, let's see, I think it's in the slide. We know from the equation, and this is an important distinction. This is a mathematical equation. 3 variables: velocity, distance, time. If you know any 2 of those, you can solve for the third one. All you need to solve an equation using one equation is one of the variables to be unknown. If one of these variables is unknown and you know the other 2, solution is simple. That's algebra. Say, in this case, we want to know how far would the car travel in 10 seconds. Well, we want to solve for this value. Right? Just move that t over here, and there you have d equals v times t. So if we know the velocity is what? 20 meters per second? In 10 seconds? Right? Remember, when you multiply those numbers together, we get 200, obviously. But what happens to the units? Well, one of the seconds is in the numerator, the other's in the denominator, so they cancel. Actually, what happens to them is you get meters times seconds divided by seconds. And that's equal to 1. Right. So you only have meters left. Okay. And I'm making a point of this one. If you have one variable that's unknown in an equation, you can solve the equation. Right? In algebra, we have examples of 2 variables that you don't know. So what do you need for a solution in 2 unknown variables? You need 2 equations in 2 unknowns. Or if you have 3 variables, 3 equations and 3 unknowns. Right? So it can get pretty messy quick. But in this class, we're going to stick to 1 unknown variable. Okay. Okay, let's see. You can see it, but I can't. So let me move it so I can see. Example, how long does it take sunlight to reach Earth? All right. Remember when we talked about problem solving? Using a word problem, right? Read the problem and look for the question. How long does it take for sunlight to reach the Earth? How long? We're talking about time. We're looking for time. And sunlight has to reach the Earth. So how does it do that? It has to traverse a distance. So we need to know a distance from the sun to Earth. We know that, don't we? Well, it's given, right? In this problem, it's given. We know, well, I know it's 93 million miles, but that's in the English system. We want the metric system, which is 1.50 times 10 to the 8th kilometers. How many significant figures there? 3. So how are we going to get that answer from that answer? Well, what relationship do we know? Well, we just studied one. Velocity equals distance traveled over a certain amount of time. We want to solve for that one. So T equals D divided by V. T goes over here, V goes over there, just like that. Okay. So do we know this one? Yep, there it is right there. How about this one? What is the velocity of light? What's the speed of light? Well, that's given also. 3 times 10 to the 8th meters per second. It's pretty fast. So we just plug in this one. And we plug in this one. Kilometers. Okay. Now, what's wrong with this problem? Units of measure. This is in meters per second, and that's kilometers, right? We're going to end up with a value that's not the answer we want. Our answer has to be in seconds, right? We can't cancel meters and kilometers. They're two different measures. We need to convert this one to meters. So how do you do that? Well, here's the simple way. What does K mean? Kilo means 1,000 or 10 to the third. That's 10 to the third, right? So now we have meters out here, but kilo is 10 to the third times that one. So now this value here becomes 8 plus 3 is 11. Now, that's 1.5 times 10 to the 11th meters is the distance from the Earth to the sun. Now we can cancel. This is in the denominator. That's in the numerator. What do we do with that seconds? Seconds, if this is in the denominator, but the whole term is in the denominator of the denominator is the numerator. So you take that, flip it. This S, seconds, goes up here in the numerator. So we know that our units of measure are going to be correct as seconds. We just need to divide this one into that one. So what's that? Well, you can use your calculator, or you can do it in your head if you want. All right. What's 3 divided into 1.5? Let's do it that way first, just to prove that I can do it. 3 into 15 is 5. But 3 is bigger than 15, so it's going to be 0.5. And prove to yourself, if you divided this into this and got that, then this times that should be that. So half of that is that. That's good. Times 10 to the what? Well, if you got 10 to the 8th in the denominator and 11th in the numerator, you subtract 8 from 11. And this is that many. So we reconcile scientific notation. 5.00 times 10 to the minus 2. 10 to the plus 2. We moved it over this way, which means this one had to come down 1. So it's 5 times 10 squared seconds. Here we go. Or 500 seconds. So nobody thinks in terms of seconds, right? What's the intuition for that? 500 divided by 60 seconds would be minutes, correct? So let's see. I'm not going to try to do that one in my head. So 500 and then divide by 60. 8.3 minutes. Now that's something we can sink our teeth into. You probably heard it said before. How long does it take? If something happens on the sun, when will you know it? 8.3 minutes later. So that's why we have some spacecraft that are orbiting very close to the sun. I think one of them's called Soho. And actually, there are several of them. And they're watching the sun. And one of the things they're watching for is coronal mass ejections. And that's a fancy word for a huge flare. A huge flare that sends out subatomic particles in our direction. And once it detects that, then those subatomic particles are not moving at the speed of light. They're moving fast, but not at the speed of light. So the communication between the satellite and Earth is much faster, and it can give us advance warning. So we can protect ourselves, protect our satellites from damage, shut them down or shield them some way, or whatever the case may be. All right. So this is just an illustration of what we just solved the problem. I will let you look at that at your leisure. All right, here's another question. What is the average speed in miles per hour of the Earth revolving around the sun? Okay, that looks like a huge problem, doesn't it? Well, until you break it down. Oops. Okay. Notice the question is speed, because if the Earth is revolving around the sun, it's changing direction. So we can't specify direction yet. We will eventually. The average speed in miles per hour of the Earth revolving around the sun. Okay. If we're going to calculate speed, we need to know what? We need to know distance and time. Right? So, do we know that? How long does it take the Earth to revolve around the sun in hours? Well, it takes 1 year, correctly? Distance is 1 year. Right? So, we want to convert that to hours, correct? All we need is a conversion factor. So we take 1 year and convert that to days, right? Then we want to convert days into hours. 24 hours in a day. So now we have hours. Okay, we'll calculate that out in a minute. Now we need what? Time. Oh, wait a minute. I'm sorry. I calculated time there, didn't I? How about distance? In miles per hour, right? How far, in this amount of time, how far does the Earth travel? What is its distance? Well, sometimes it helps to draw a picture. So there's your Earth. There's the sun, and it's got to go around like that. What is that? It's a circle, correct? So what's the distance around there? The circumference of a circle is equal to pi times diameter. So what's the diameter here? Well, we know the radius, right? The radius is 93 million miles. What's the rate? What's the diameter? Well, it's 2 times that. So we say the distance is equal to pi to r. Right? We just substitute that value right here. And that gives us our distance. Okay? So that's what we're doing here. Convert 365 days to hours, which is what we did here. Earth's radius is that. Right? So 8760 hours. Okay. 8760 hours. That's 3 significant figures. And then distance is 2 pi r, 3.14 or whatever the pi is in your calculator, times that radius, because 2 pi is diameter. Okay? So here we have distance there and time, right? And that is 0.00667 times 10 to the 7th miles per hour, right? So let's put that in standard notation, right? That is without powers of 10. Convert that to standard notation, and it turns out that the Earth is moving at 66,700 miles per hour. That's also known as orbital velocity. Actually, it's orbital speed. All right. I don't think I'm going to get finished in an hour. So we just keep plugging along. All right. Next concept. What's the average speed in miles per hour of a person at the equator as a result of the Earth's rotation? Okay. So what's the radius of the Earth? We know that it's a similar problem because somebody is moving in a circle. First, we did it for the Earth moving in a circle around the sun. That's revolving. Rotation is another concept. Revolving is an object moving around a center of some sort. Rotation is an object spinning on an axis. So that's the Earth spinning on its axis at the surface of the Earth. If we take the radius to be 4,000 miles, then how far does a person move in one day? 24 hours, right? So that'd be those many miles per how many hours? 24 hours, right? So 2 times r is the diameter. That gives us times pi then is the circumference, and then divided by 24 hours. Okay, you're moving, and this is an average value, right? The Earth and many heavenly bodies, because of the way they spin, and it tends to draw the equator out because it's moving faster than the poles. It's known as an oblate spheroid, which means it's fatter around the middle. So this is an average. Well, no, I take that back. I reread the problem. Person at the equator. So we're saying at the equator, the radius of the Earth is 4,000 miles. I think that's just to simplify the problem. But you're moving at a little over 1,000 miles an hour. So why would we want to know that? You know, why would any scientist want to know that? Well, think about it. If you're trying to throw a rocket up into space and orbit the Earth, and the Earth is rotating this way, right, west to east at 1,000 miles per hour, but you're going slower speed up here at this latitude, you may only be going 800 miles per hour. Okay. Well, if you do that and you want to put a satellite in orbit, it just makes sense. You want to get every advantage possible. So you try to launch your rocket near the equator, southern latitudes. It's already got 1,000 miles an hour going for it. So your rocket doesn't have to work as hard to get it to escape velocity, orbital velocity. That's why Cape Kennedy is located in Florida. It's further south, and its start velocity is closer to 1,000. There are some commercial companies that are launching from Texas, right? That's further south. And some from Southern California, that's further south. The French, or actually the European Space Agency, launches their rockets from almost on the equator in French Guiana in South America. So they've got even a better advantage. They're right on the equator. They've got the maximum boost that you can get for a rocket, for the satellite, before the rocket has to add velocity. Okay, let's move to another concept. Acceleration. What do we mean by acceleration? Acceleration, the concept we start with is velocity. Remember, we had uniform velocity and uniform speed in the beginning. But now we're going to let the velocity change at a uniform rate. In other words, we may start off here, our car may start off at 10 miles per hour in that direction. But by the time it gets to here, it's 60 miles per hour. Okay, and it's traveled a certain distance. Well, I don't know. We'll make something up. We'll let the problems work themselves out. We'll not put a value yet. So if you go from 10 miles per hour here to 60 miles per hour there, what has changed? The velocity has changed. In that chain, we have a change in velocity. Well, how long did it take you to get there? Well, whatever the time is. We don't know what the time is. But you would divide this by the amount of time it takes to get from this velocity to that velocity. That is acceleration. Now, as a matter of fact, this is a positive acceleration. So the v here would be a positive value. But if we went from 60 to, say, 0, you were stopping, then you would go from a higher velocity to a lower velocity, and then this value then would be a negative acceleration, which we often call deceleration. But in scientific terms, acceleration is a change in velocity. It doesn't matter whether it gets bigger or smaller. Now, you can increase the magnitude, or you can speed up, or you can slow down, or you can change direction. If you change direction, velocity is a vector quantity. So if you change direction, you're changing velocity, right? So if you change velocity by changing direction, the speed can be the same. So going through a curve, you're actually accelerating. Okay. I've already put that on the board. Change in velocity over time. And that's an average. This is an average acceleration. Like I said before, we're not going to mess with variable accelerations because that requires some advanced math, and that's beyond this course. But here's their bar over A. Sometimes small a is good for acceleration. Yes. And v sub 0 is initial or original velocity. Doesn't have to be 0. Can be anything. But if you subtract that from the final velocity, then you get the change. And you could come up with a negative value over a certain period of time. And that's how you calculate the average acceleration. Now, notice the units of measure. What are the units of measure for velocity? Well, velocity is in standard measurements, or SI units, are meters per second. But time is in seconds. So the denominator of the numerator is the denominator. So you get this one times that one. And the units for acceleration are meters per second squared. Okay? It's just that simple. Understand it or memorize it, whatever you have to do. Okay. So one situation where there is constant acceleration, and everybody knows it intuitively, although only scientists do the calculations, is the acceleration due to gravity, right? And if you are at a certain height on a platform and you jump off, you will change your velocity as you approach the ground. You get faster and faster and faster and faster. You are accelerating. And this is the rate of your acceleration, 9.8 meters per second squared. And that's for any object near the surface of the Earth. As you get really, 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 really high, like out in space, then this value will change. But near the surface of the Earth, 9.8 meters per second squared is the acceleration of an object due to gravity. And that's why you feel weight, why you feel the pull as you move about on the surface of the Earth. This illustrates that. If you drop something from a height, in the first second, the object will now be going at 9.8 meters per second, right? Because, okay, let's break this thing down. Acceleration equals change in velocity over time. There's an equation. So if this value is 9.8 meters per second squared, and this velocity, the initial velocity, is 0, V initial is equal to 0, what is the final velocity? That's the question. How long did it take? 1 second. Okay? So we want to solve for this value right here. Well, that's a 0, so it goes out. This second goes over here times that, so we have 9.8 meters per second squared times 1 second. That second cancels one of those, and we get 9.80 meters per second equals the velocity after 1 second. Okay? Now, how far did it travel? Well, that's another question. And there's a formula for that. And we'll derive it in just a second. But this is the distance traveled, right? After 1 second, it's going that fast, but it's only traveled 4.9 meters. Notice that's half of 9.8. After 2 seconds, then it's going 19.6 meters per second, but now it has traveled 19.6 meters. After 3 seconds, it's actually going 44.1 meters. Now, this is not to scale, I don't think. That doesn't look like the right difference in distance, right? So that the distance is not to scale. When you hit the ground, after 4 seconds, you're going 90.2 meters per second from a height of 78.4 meters. Okay? It's just that simple. We can calculate your final velocity right as you hit the ground. The ball hits the ground, excuse me. The guy didn't jump, the ball fell. Okay. So here's another example. A race car starting from rest accelerates uniformly along a straight track, right? Well, it's a drags race, reaching a speed of 90 kilometers per hour in 7 seconds. Actually, that's not very fast. 90 kilometers per hour. We looked at that speedometer earlier. 90 kilometers is close to about 60 miles an hour, right? So for a race car, that's not real fast. And to do that in 7 seconds, that's not good either. I mean, we've got production cars, sports cars, that will go to 60 miles an hour in 3 seconds. So this is just hypothetical. Maybe he's got water in his gas tank, who knows? What's the acceleration? If we're going from 0, starting from rest, initial velocity is 0, right? Let's write that up there. Initial velocity equals 0 kilometers per hour. And final velocity is 90 kilometers per hour. Let's give those 2 significant figures there. How long did it take to get there? 7 seconds. So the change in time over that distance is 7 seconds. So we can calculate the acceleration. We just say final minus initial divided by the time. There you go. There you go. Final minus initial. Meters per second. Oh, find the acceleration. Okay. The acceleration is they want to change the velocity to meters per second. And that's based upon this wanted A in meters per second. The problem didn't say that initially, but with given and extra information, all right, we need 25 meters per second. So you use a conversion factor. And here's the conversion factor from meters per second, kilometers per hour. And I can show you how to do that, but it really would take too much time. You can figure that yourself, right? This is the metric system. So all you have to do is take kilometers per hour, just 1 kilometer per hour, and convert kilometers to meters and hours to seconds. Maybe we should do that. Let's do that, right? Because this is a situation where you're changing 2 units of measure. And that's an important technique to develop. So 90 kilometers per hour. When you do a conversion where there's more than 1 unit to be changed, do 1 unit at a time. So let's change kilometers to meters. 10 to the third, or 1,000 meters, is equal to 1 kilometer. Okay, we got meters. Now we need seconds. How many seconds in an hour? Well, we could do a chain conversion, 60 seconds in a minute and 60 minutes in an hour. But I know that when you multiply those together, you get 3,600 seconds in an hour. Okay, so that cancels hours and leaves us with meters per second. So if you multiply actually, we're going to convert 90 kilometers per hour to meters per second. So 90 times 1,000, and then divided by 3,600 is 25 meters per second. I just verified that, 25 meters per second. Okay, so now we have velocity in meters per second. Since the initial is 0, we don't have to convert that one, right? 0 is 0 in any units of measure. Now we have the time, right? So we can divide this by that, and we get 3.57 meters per second is the acceleration of that vehicle, that car. That's not a race car. I bet my Toyota van could beat that race car. Anyway, that's the answer, 3.57 meters per second squared. That's the giveaway. Second squared, that's acceleration. Okay, now, we know this equation is true, but maybe what we really want to discover is if we know the initial velocity of the object, and then at that point, at that velocity, it begins to accelerate for a certain amount of time. Then we can calculate the final velocity. So we'll know what the final velocity is. If you go back to that original problem, what was the initial velocity of that ball? 0. So that becomes 0. And then the final velocity is simply acceleration times time. So 9.8 meters per second squared is acceleration due to gravity for 4 seconds is 39.2 meters per second. That's where that number came from. Let's go back. Right here. 39.2 meters per second came from that equation. All right, there's no mystery. It's simple math based on the physics. Okay, let's get back over here where we were. Okay, if the car in the preceding example continues to accelerate at the same rate for 3 more seconds, what will be the magnitude of its velocity in meters per second at the end of this time? Okay, we know what the initial velocity is because we know that it's going 25 meters per second at the end of that amount of time, 7 seconds. So that's our initial velocity, our new initial velocity, right? What we want to know is the final velocity. But we have an equation, which is the initial velocity. They say v sub 0. I like v sub I, initial velocity, plus acceleration times time. So for another 3 seconds, it accelerates at the same rate, which was, let's see, 3.57. There it is, 3.57 meters per second squared. So one of those seconds cancels and leaves us with meters per second. That's good. So this initial velocity is 25 meters per second. Same units, we can add them together. So all you have to do is multiply 3.57 times 3 and then add 25 to it. And that's 35.7 meters per second. Okay. I like to do these on the board sometime and see if my slide agrees with me. Oh, did I say 3 or 10 seconds? Exceeding, accelerate at the same time for 3. Oh, for 3 more seconds. Okay. Here's what they're doing. They're going from 0 initial velocity with that acceleration for 10 seconds, 7 plus 3, right? That's another way to solve the problem. Let's see if they get the same answer as we do. 35.7 meters per second. See? Get the same answer working a different way. All right. Let's see, this problem is acceleration is a vector quantity since velocity is a vector quantity. Yes, acceleration is a vector quantity. simply because velocity velocity divided by time means that you don't lose the direction. Velocity is a vector quantity, so acceleration has to be a vector quantity. Okay, this one's accelerating, this one's decelerating. It's going from 30 kilometers to 0. This one's going from 10 to 20. That's acceleration. This by convention is deceleration, but in scientific terms, it's still acceleration. It's just negative acceleration. Okay, here we go again. Special case associated with falling objects. The acceleration here due to gravity is 9.8 meters per second, just like we said earlier. And the vector is toward the center of the Earth. So when gravity is involved, the vector direction is toward the center of the Earth. All right. If we graph the velocity, from that previous example in these points over time, then we see an increase in velocity. See, the velocity is changing over time. So in graphical terms, what is acceleration? Acceleration is the slope of that line. Remember what a graph represents. A straight line of a graph is like this. If this is the X and this is the Y, a straight line is defined by two things. Yeah, two things. This is the y-intercept. I'm giving you a crash course in graphics. And this is the slope, is equal to rise over run, change in y over change in x. In our case, this is change in velocity. And this is change in time. Okay? So if we divide this, which is the slope, this divided by that is the slope, then the slope is equal to acceleration, right? So if you graph the velocity against time like this, and the slope of the line then is acceleration. Sometimes that's convenient. Suppose your velocity is not uniformly changing, right? That's one approach. If you have a curve here, then you can tell what the instantaneous velocity is. Excuse me. Yes, the instantaneous acceleration based on any point of that curve. All right, we beat that horse enough. Let's move on. Okay, what we have studied so far is displacement, distance, displacement, time, velocity and speed, the difference there, and acceleration. These calculations are all under ideal situations, right? And what I mean by that is there's nothing that is interfering with the motion. And the major interference in motion on the surface of the Earth is friction, right? We have to take friction into account in the real world, but in the ideal world, we can ignore that. And for objects moving through air, as long as they don't have a lot of wind resistance, we say, then the ideal approaches the real. The only way you can actually get ideal is to conduct your experiment in a vacuum, and that's what this device is. It's an evacuated cylinder. This coin and this feather are falling with the same acceleration, and there's no wind resistance. So they will hit the bottom at exactly the same time. It doesn't matter how big they are. Their motion is determined by the acceleration of gravity, not by the mass of the object. All right, so the frictional effects set aside, these two objects will strike the bottom of this container at the same time. Now, Galileo proved that concept, that physical property, in 1590. But he used two objects that he reasoned would not be significantly affected by friction. Just two big balls, heavy balls. One small but heavy, and one large but heavy. And that way he minimized the effect of wind resistance. Right? And let me go to this slide. He did it from the Leaning Tower of Pisa. Now, this bell tower that was built in Pisa, Italy, wasn't built that way on purpose. The engineers, the architect, and the builders didn't take into account the foundation upon which the tower was built, and over time it started to lean. It's since been stabilized, but it's still leaning. And at the time, Galileo needed some way to, some height from which to drop his objects without fear of striking the base of the structure. And the Leaning Tower of Pisa was perfect because it leaned out and he could drop these things, and he found that they hit the ground at exactly the same time. Now, that concept was proven on the moon, where there is no air. Astronaut David Scott, in the Apollo 15 mission in 1971, that may have been the last one. Yeah, I think that was the last mission. Anyway, he dropped a hammer and a feather on the surface of the moon, and they hit the ground, hit the moon surface at exactly the same time. So he confirmed Galileo's experiment in a vacuum. Okay. So what about the distance? We have calculated the final velocity of an object dropped in Earth's gravity. What about the distance that's traveled as the object is dropped? Well, I'm not going to go through derivation. It would just take too long. But the distance traveled is related to the acceleration of gravity times the time it takes to do that times 1/2. So that's the distance traveled. How long does it take to travel that distance under the influence of this acceleration of gravity? And actually, that equation is not limited to gravity. It's actually derived from this one. Let's see, excuse me. Distance equals 1/2 a t squared. So any acceleration can be substituted in there. It's just that this is a special case where we have the distance where we know what g is, 9.8 meters per second squared. The amount of time it takes in this formula will give you the distance. All right. So let's say a ball is dropped from a tall building. How far does the ball drop in 1.5 seconds? Okay, 1.5 seconds, 9.8 times 10, 9.8 meters per second squared. And this 1.5 seconds is squared also, times a half, right? So there are your given values. This is the solution. You substitute this acceleration due to gravity, 1.5. And remember, when you process a mathematical expression, the number undergoes the change and the units of measure undergo the change. So it's 1.5 squared and seconds squared. All right. So that's what we get, 2.25 seconds squared. And then both second squareds cancel and leave us with meters, which is the distance. So it's useful to check the units of measure, right? If you're expecting meters over here and the cancellation doesn't work over here, then there's something wrong in your calculation, right? Look for those clues before you try to shove a square peg in a round hole. And the answer is 11 meters. So in 1.5 seconds, that object will have traveled 11 meters. What's the speed of the ball in the previous example? 1.5 seconds after it's dropped. Okay, we know that or g, acceleration due to gravity, is this value, time is that value, and we have our equation, final velocity. Initial velocity is 0, acceleration is 9.8, and time is 1.5 seconds. So we can calculate that the speed of the ball after 1.5 seconds is 14.7 meters per second. Okay. All right. This just illustrates the point that velocity is proportional to time. So here's time, and this is distance. Right? So this is not velocity like the previous graph. This is distance. So velocity, in our case, is uniform. In other words, it's a straight line, and the time traveled in this distance is velocity, slope of that line. But if we also plot the distance traveled under the acceleration of gravity, this is uniform velocity. But if we introduce gravity, then we find that the distance traveled is proportional to time squared. And we get that from the equation, of course. We go back here. Proportional distance traveled is proportional to time squared, whereas velocity is proportional to time. Okay. So here's another twist on this problem. Suppose you throw a ball up in the air, straight up in the air, right? What happens to the ball? Well, the ball accelerates, but in the wrong direction. Right? It's still under the influence of gravity. So as it goes up, it actually slows down until it reaches a point where the velocity is 0. That's exactly the opposite situation from dropping a ball from that height. So when it comes back down, how fast will it be going? It'll be going at the same speed, same velocity as it was when you threw it up. See? Throw it up at this velocity, then the final velocity minus the initial velocity gives you the change in velocity, right, over time. And then coming back down, it starts at that velocity and ends at the initial velocity, which is a substantial number. How long does it take to traverse that distance? Well, it takes it a certain amount of time for this transition, and it takes the same amount of time this transition. So if you calculate the time for this to occur and double it, then you know how long it takes for the ball to go up to the height and come back down. Acceleration coming down is positive, going up is negative. All right. Now, those were scenarios for linear motion. We're going to take a break from linear and move to circular for a little while. And we'll come back to linear and talk about vector analysis of non-straight motion, where you throw it off at an angle. But for now, we're going to talk about uniform circular motion. That's the key, uniform. What's uniform? That means it's moving at the same speed in a circle. So the speed at any one point around that circle is the same. But it is accelerating. Why? Because it's changing direction. And remember, velocity specifies direction. So if you change direction, you are accelerating. All right? That might be a difficult concept, but it is true. So what is the direction of that acceleration? If you're going around if something is moving in a circle, some object out here, and it's moving in a circle. Right? At each point along here, we can determine a speed. Well, actually, it's a velocity because it has a direction associated with it. It's going at a certain velocity, like that. And this way, notice that the velocity is this way, and over here it changes, like that. It's the same speed, but it's a different direction. So what direction did it change? It changed toward the center. So this is known as centripetal acceleration or centripetal motion. It's directed toward the center. At right angles to the velocity. If we carry this out here, that's a right angle. Okay. One way to look at that is for a race car going around a curve, right? Its velocity here, right here, velocity 1, but it changes when it gets to this one position, velocity 2. Now it's going this direction. See, that line is parallel with this one, and this line is parallel with that one. So the change in velocity is from here to here. Over here, the change in velocity is from there to there. So now we have a change in velocity divided by how long did it take to get there. Of course, the car is maintained in that circular motion by the friction from its tires, right? If you don't have that, then it's going to go out like that, straight out at that velocity. Now, the formula for calculating the centripetal acceleration is just this. You know the velocity of the car at any one time. As long as it's uniform, then all you need is the radius of the circle. And the radius of the circle divided into the velocity squared is acceleration. So we don't have time to derive that now, just memorize it. Uniform circular motion produces an acceleration that is calculated as velocity, or the speed at any one instant, squared, divided by the radius. Okay, so what does that mean? That means acceleration is proportional to the square of the speed. So if you double the speed, you quadruple the acceleration. Or if you decrease the radius of the circle, then you increase the acceleration by the same proportion. It's exactly proportional. If you decrease the radius in half, then the acceleration doubles. Okay, here's an example. That car is moving at 12 meters per second on a circular track with a radius of 50 meters. So let's calculate its centripetal acceleration. Okay, there's your velocity. Remember, we're going to square it. Square the velocity, divide by the radius, and we have a centripetal acceleration of 2.9 meters per second squared. Now, to put that in context, remember when we said G is a special value for gravity, meters per second squared. All right? So if this acceleration is 2.9 meters per second, how is that related to G? Well, if we do 2.9 times 9.8 and meters per second squared divided by meters per second squared, that cancels. Then let's say 2.9 divided by 9.8. 0.9 enter 9.8 divide is 0.30. 0.30. And that's a dimensionless number. But we want to relate it to something. We want to explain what it means. So it's related to this G. So often we say xg. It's a third of the acceleration of gravity. And that gives you some idea as to what type of motion is being directed toward the center. It's not the same motion as 9.8. It's not that much. It's only a third of that. And you'll see in, let's see, Car and Driver magazine, for instance, they always report how well a car can manage they call it in a skid pad. As you go around there, when the tires start to break loose, then you sort of let up and make sure that you always have contact with the ground. And then there's an instrument inside the car that measures the centripetal acceleration in that curve relative to G. And it'll spit out the number in G's. Now, very expensive sports cars will do 1 G or more in a curve. And you can feel it, right? Anytime you go into a curve, you can feel it pulling you. It's trying to make you go out, but there's a force that's keeping you, it's friction in your seat, keeping you in your seat. But it's trying to make you go out, and the force that's holding you in there is centripetal, holding you toward the center. Right? So most production family cars are going to be in that neighborhood. Right? Okay. What's the centripetal acceleration in meters per second squared of the Earth in its nearly circular orbit around the sun? Okay, so we've got this radius, we've got this velocity, which we calculated earlier. And then if we plug those values in, we check our units of measure. Meters here, seconds here. Okay, we're good. So velocity will be squared, divided by radius. And there we have 6 times 10 to the minus third meters per second squared. So that's a pretty small number, isn't it? Very small number, right? 6 times 10 to the minus 3 is 1, 2, 3 meters per second squared. So that's 6,000th of a G. Well, not of a G, excuse me. 6,000ths of a meter per second squared. Okay, now let's go back. That's uniform circular motion. Let's go back to linear motion, only now we're going to use vector analysis. That's the fancy word for it. Vector analysis of a projectile. So what's a projectile? A projectile is anything that's thrown. You can throw it with your arm. You can throw it with a golf club, striking a ball. You can throw it by shooting an arrow. You can have a cannonball coming out of a cannon. That's a projectile. And we want to analyze how do we make sense of projectile motion? That's the key. The fact of the matter is, when that projectile is set in motion, there are 2 independent motions that are taking place at the same time. You have a horizontal, we call it component. A horizontal component, say this object is launched like that at an initial velocity of 10 meters per second. Okay? Trigonometry will tell you how much of that is this way and how much of that is this way. So some of it is going to be horizontal. Some of it is going to be vertical. The vertical is going to be subject to gravity, right? It'll go up to a certain height and then it'll start back down. But because it's moving this way also at uniform velocity, it looked like a curve. It's actually a parabola. It'll go like this. And the part that goes up and back down is this part. And the part goes from here to here, right, is this part. Okay? Now there's a way to analyze that. All you need to know is the angle. What's the angle at the point of release? And then using trigonometry, we can tell how much of it is this and how much of it is that. Or you can draw it out on a piece of graph paper and say this vector represents 10 meters per second, right? So you have 10 units here. And then you draw this one out to where that's perpendicular and this one out to where that's perpendicular. Measure that length, measure this length. And you can do it on graph paper without calculation. Okay, so what this is showing you is that when you drop a ball straight down, it's under the influence of gravity. But if you toss the ball out from that level at the same time, then it will undergo gravity, but it'll also have a horizontal component like this, right? And notice these happen at the same time all the way down to the bottom. But now, since you had a horizontal component the ball is not here with the red one, it's over here. This travel was due to the horizontal, and this travel was due to the vertical. This is another example. Right? In some circles, this is known as ballistics. Right? If you're a hunter and you know how to zero in your rifle before hunting season, then you know that when you shoot your rifle, right? Shoot your rifle at a target, it's going to drop. If you aim and your scope is exactly parallel with your barrel, then your bullet goes like this and it ends up over here. It drops because of this influence of gravity. So what do? You compensate, right? You adjust your scope. Say you set it at 200 yards. Your target is 200 yards out. So you adjust your scope so that the scope is set so that when you put your scope here on the target, your barrel is actually elevated. And the bullet goes like this, strikes the target at 200 yards. That's called zeroing your scope. And this is the reason you do it. You're compensating for drop due to gravity. Every hunter knows that. All right. All right, here's the case like this one, where you have this object like that, and these are the different components. This is the vertical component subject to gravity. This is the horizontal component, uniform velocity. Those two added together will give you the information that you're looking for. Range, perhaps. Okay, how would you do that? Well, if you know the horizontal component, then for all intents and purposes, it'll just keep going. It'll never stop, right? Because it doesn't know when to stop. So what you need is the vertical component, because you do know from acceleration of gravity what's going to happen on the vertical. It's going to go up, and in the same amount of time, it's going to come back down. So you measure how long it takes to get down here and double it. That's the time. So you have a velocity times a time gives you a distance. So once you find the time from this component, you can apply it to this component here, and that tells you the range. That's when your object hits the ground. Football is another example. I'm not going to labor this one because I'm already way over time. This is a good lesson. If we ignore all types of friction, wind resistance, everything, say it's a quiet day, and we can ignore the resistance of air to our golf ball, what will give you the maximum range? As a matter of fact, it's an angle of 45 degrees. So part of the velocity is this direction, and then the other part is this direction, and it turns out that 45 degrees gives us the maximum amount of hang time. And the maximum hang time means longer range, the maximum range. Now, in reality, we do have the influence of friction. So if you compensate for friction to get the maximum range, instead of 45 degrees, if you do 45 degrees, friction is going to actually slow your horizontal down. So the time it takes to go up and back down might be the same, but because the friction has slowed down your horizontal component, that amount of time is applied for a shorter distance, and it drops here. So if you lower your angle, then you put more initial velocity into the horizontal component and take away only a little bit from the vertical. And that adds to your range. Now, you're never going to get, with air friction, you're never going to get the theoretical range of a 45-degree angle. But you will maximize at the Earth's surface, under most conditions, 38 degrees will give you the maximum range. All right. So what other considerations do we need? Well, we've talked about the angle of release. That's important. If we're talking about golf or baseball or football, the spin of the ball matters, right? If you put a spin on a golf ball, instead of going in a straight trajectory with an arc, it's going to curve, right? Because the spin of the ball interacts with the air to apply an unbalanced force in one direction or the other. Or if you're throwing a fastball, right? A fastball tends to rotate backwards, which builds up pressure underneath the ball and decreases pressure above the ball. So the ball tends to rise and compensates in the process. So if you throw it fast enough and get the spin right, the ball will actually rise. That's why catchers' mitts are so big, because when that ball comes, you need to have lots of area to catch the ball. And it's even more true for knuckleballs, because knuckleballs had no spin. So they could go anyway. That's the danger of a knuckleball. But never mind there, we're moving on. The size and the shape of a ball or the projectile makes a difference, because the frictional interaction is greater for a larger area. If there's any wind involved, headwind, crosswinds, right? Here we are back to hunters or snipers. You understand the effect of wind. If it's a short distance, the wind makes very little difference. But if it's a long distance, like 600, 800, 1,000 yards, the wind becomes extremely significant to the trajectory of the bullet. Weather conditions can also impact the performance of a projectile in motion. Humidity makes a difference. Well, obviously rain, because droplets are going to be banging on your projectile and slowing it down, driving it down. Snow, whatever, other weather conditions. Temperature makes a difference too. Hotter air is less dense, so a bullet will travel farther with less drop in hot air. Cold air is denser, so it'll drop quicker because denser air has more friction. Humid air is lower pressure, so it should be less dense. But then there's the issue of, is that humid air, does it produce a fog? If it produces a fog, then you actually have physical droplets that are interacting with your projectile, and they will slow the projectile down. Altitude makes a difference, right? The higher you go, the less dense the air, so less friction. And usually though, altitude doesn't make a difference in the acceleration of gravity until you get really far from the Earth. So basically, altitude has to do with air friction, density of air. And then initial velocity. That is always important, right? If you have a batter who's weak, you'll never hit it hard enough to make the arc land outside the fence for a home run. But a batter who can hit the ball harder and the initial velocity is harder, the ball will travel and its range will be beyond the fence. Home run. Or for golfers, they call them big hitters. The big hitters stand at the tee and they whack the ball with more force than other golfers. And they send their initial, their tee shot way down range compared to their competitors. Okay, these are equations that we've introduced. You need to memorize these. They're not that many. And the best way to memorize them is to use them. Work problems. Work as many problems as you can get your hands on. You've got sample problems in your textbook. You've got homework problems. Your two best friends in science are curiosity. You always want to know more about something. That is never a bad thing. And the other is boredom. If you're bored working problems of a certain type, then you have worked enough of them. You recognize them, you know how to work them. They're not fun anymore. So you could pass those up and go to problems that aren't fun anymore. Those are the hard ones that you don't know very well. Curiosity and boredom, your two best friends in science. So here are your equations. Some chapters will have lots of math in them and some chapters will have very little math, right? There's lots of math in this one. There's math in chapter 3. There's some math in 4, 5, 6 on up. When we get to Kepler's laws of planetary motion, there's some math there. But memorize these equations and work as many problems as you can get your hands on and you have time for. And that's it for chapter 2.